Let us now learn about orbital diagrams. Let us take a look at this question. Draw the orbital diagram for oxygen atom. Before you can draw the orbital diagram, the first thing to do is to write the electron configuration for the atom. For oxygen, the electron configuration is 1s2, 2s2, 2p4. Let us now represent this diagrammatically. Let us assume that this is the energy axis. The 1s orbital has 2 electrons in it, and it is the lowest energy orbital. So let us represent it right here. 1s orbital. It has 2 electrons. Now, according to the spin quantum number, if 2 electrons are occupying the same orbital, one of them will have to spin up, which will represent like that. The other will have to spin down, which is represented like that. This is a question. Why? A spinning electron will generate a magnetic field. So if this electron is spinning like this and this one is spinning like this, they will generate opposite magnetic fields. The opposite magnetic fields will then attract. That is similar to having 2 bar magnets placed side by side like this, with one of them having its north pole up here and the other one having its south pole up here, and the south and the north are like this. Remember, the north pole of a magnet will attract the south pole of the opposite magnet. So, although the 2 electrons are negatively charged, because they are spinning in opposite directions, they can still occupy the same region of space. So, for the 1s orbital, we're going to represent the 2 electrons like this. After the 1s orbital, we have the 2s orbital, which also has 2 electrons. The 2 electrons will also be spinning in opposite directions. So that represents 2s orbital. And then after the 2s orbital, we have the 2p orbital. Now, the very first thing to remember about any p orbital is that a p orbital has 3 orientations: px, py, and pz. So we should have 3 orbitals. These 3 orbitals will be equal in energy because they are degenerate. That is the term. They are degenerate orbitals. Degenerate orbitals will have equal energy because although they have different orientations, they are orbitals of 2p. Each orbital can only hold a maximum of 2 electrons. That is why a p orbital can only hold a maximum of 6 electrons. But in oxygen, we only have 4 electrons in the 2p orbital. So this is then the question. How do we distribute 4 electrons among 3 2p orbitals? That question is answered by what is known as Hund's rule. What is the Hund's rule? Hund's rule says that we should place 1 electron in each orbital before we start pairing them. Place 1 electron in each degenerate orbital before pairing. What does that mean? We have 4 electrons in the 2p orbitals, so we are first going to give each of them 1 electron, and then we will begin to pair. In the case of oxygen, we have only 4 electrons to be distributed among the 3 degenerate p orbitals. So this is the orbital diagram for oxygen. Let us practice with another one. Let us draw the orbital diagram for silicon. Again, the first thing is to write the electron configuration for silicon. The electron configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Let us now draw this diagrammatically. The 1s2 orbital is the lowest energy orbital, and the 2 electrons will be spinning in opposite directions. The next higher energy orbital is the 2s orbital, and the 2s orbital also has 2 electrons spinning in opposite directions. After that comes the 2p orbital. The 2p orbital has 3 degenerate orbitals because every p orbital has 3 orientations. So we have 3 degenerate orbitals. In silicon, the 2p orbital has 6 electrons. According to Hund's rule, we will fill each orbital singly, and then we will pair them up. And then we move on to the 3s orbital. The 3s orbital has 2 electrons in it. Both of them will spin in opposite directions. And then we come to the 3p orbital. Any p orbital will be triply degenerate. We only have 2 electrons in the 3p orbital, and according to Hund's rule, we will try to fill up singly before we pair. So since we have only 2 electrons, that will be the orbital diagram for silicon.